Here is today's problem. We are given an equation containing two square roots. The first expression is the square root of x minus 8. The second expression is the square root of x plus 8. These two roots are added together to make a single sum. This entire sum is equal to the constant value of 8. We can see that the variable x appears twice in this problem. We will start our solving process by defining a brand new algebraic variable. We will define a new variable and assign it the letter u for our calculations. We choose to set this variable u equal to the very first term in our equation. This means we write u equals the principal square root of x minus 8. Our immediate goal is to rearrange this definition to isolate the variable x. We want an expression that gives x purely in terms of our new variable u. To achieve this isolation, we must remove the square root symbol from the right side. The standard mathematical procedure to eliminate a square root is to square the term. Therefore, we must apply a squaring operation to both sides of our new definition. We take the variable u on the left side and multiply it by itself to square it. This calculation simply gives us the algebraic expression u squared on the left. Next, we take the entire square root expression on the right side and square it. Squaring a principal square root perfectly cancels out the radical symbol. This operation leaves only the expression that was originally inside the root. The inside expression is exactly the variable x minus the number 8. We have now derived a new intermediate equation reading u squared equals x minus 8. We are now very close to having the variable x completely isolated on one side. On the left-hand side, we take u squared and add 8 to form a new binomial. This results in the combined algebraic expression of u squared plus 8. On the right-hand side, we have x minus 8 and we add 8 to that group. The negative 8 and the positive 8 add together to make exactly 0. This cancellation leaves the variable x standing entirely alone on the right side. We have successfully found an explicit formula for the variable x in terms of u. The formula states that x is identically equal to the quantity u squared plus 8. We will now use this isolated x formula to rewrite the original mathematical equation. We can replace this specific instance of x with our newly derived algebraic formula. We carefully substitute the binomial u squared plus 8 in place of the letter x. The expression inside the second square root now reads u squared plus 8 plus 8. We must simplify this new inner expression by combining the constant numerical terms. We have two positive 8s that need to be added together algebraically. Calculating the sum of 8 and 8 gives us exactly 16 as the result. We replace the two 8s inside the radical with this single number 16. The expression entirely inside the second root is now u squared plus 16. This means our complete second term becomes the square root of u squared plus 16. We are finally ready to write down our entire original equation in terms of u. The first term of the equation was simply defined from the start as the variable u. We just determined that the second term is the square root of u squared plus 16. The original problem stated that the sum of these two terms must equal exactly 8. Our newly transformed equation is u plus this new square root equals exactly 8. To solve this new equation, we need to isolate the square root expression completely. We want the radical term to be alone on one side of the algebraic equals sign. We can accomplish this by moving the solitary variable u over to the right side. We subtract the variable u from both the left and right sides of the current equation. On the left-hand side, we have an initial positive u and we subtract a u from it. The positive u and negative u cancel each other out to leave absolutely nothing. This cancellation successfully leaves the square root term completely by itself. Our equation now has the square root on the left and 8 minus u on the right. We must proceed to eliminate the square root symbol from our current equation. The established mathematical technique to remove a square root is to square the term. We will apply a squaring operation to the entire left side and the entire right side. We place parentheses around the square root on the left and square that whole quantity. We also place parentheses around the binomial 8 minus u and square it entirely. Squaring the radical on the left side performs a perfect cancellation of the root sign. This operation simply extracts the expression that was living inside the square root. The extracted expression on the left-hand side is exactly u squared plus 16. On the right-hand side, we are faced with expanding the binomial 8 minus u squared. Squaring a binomial means we must multiply the group by an identical copy of itself. We must multiply the quantity 8 minus u by another quantity of 8 minus u. We will use the standard distributive property to perform this binomial multiplication. Every term in the first binomial is multiplied by every term in the second binomial. We first multiply the leading number 8 by the other leading number 8. The multiplication of 8 and 8 yields a product of exactly 64. Next, we multiply the first number 8 by the negative variable u in the second group. This particular multiplication gives us a result of negative 8 times the variable u. Then we multiply the negative variable u from the first group by the second number 8. This yields another result of negative 8 times the variable u for our expansion. Finally, we multiply the first negative variable u by the second negative variable u. When we multiply two negative quantities together, the resulting product is positive. Multiplying the variable u by another u produces a positive u squared term. We have now completed all 4 individual multiplication steps for our expansion. We can write down all of the resulting terms in a single long algebraic expression. The right side is 64 minus 8u plus u squared. We notice that there are two middle terms that both contain the single variable u. We must combine these two like terms together to simplify the overall expression. We take the first negative 8u and subtract another 8u from that amount. This calculation yields a combined total of negative 16 times the variable u. The simplified right side is 64 minus 16u plus u squared. Let us now write down our complete updated algebraic equation using these new results. The left side of the equation is still the binomial expression u squared plus 16. The right side is the trinomial expression 64 minus 16u plus u squared. We set these two algebraic expressions equal to each other to continue our problem. Looking closely at the equation, we can spot a u squared term on both sides. This presents an excellent opportunity to simplify our mathematical equation further. We will subtract a u squared term from both the left and right sides of the equation. On the left side, subtracting u squared removes the squared variable term completely. On the right side, subtracting u squared also removes that squared term completely. This simultaneous cancellation makes our current algebraic equation significantly simpler. Our new and simplified equation is simply 16 equals 64 minus 16u. We must now isolate the variable u in this straightforward linear equation. The term containing our variable u currently has a negative sign attached to it. It is often mathematically easier to work with terms that have positive coefficients. We can make the term positive by adding 16u to both sides of the equation. This action physically moves the variable term over to the left side of the equals sign. The updated algebraic equation reads as 16u plus 16 equals 64. To continue isolating the variable u, we must remove the constant 16 from the left. We subtract the integer 16 from both sides of our current mathematical equation. On the left side, the positive 16 and the subtracted 16 perfectly cancel out. This cancellation cleanly isolates the term 16u completely on the left-hand side. On the right side, we must carefully execute the subtraction of 16 from 64. Subtracting 16 from 64 leaves us with a final resulting value of 48. We have arrived at the simple algebraic equation of 16u equals 48. The variable u is currently being multiplied by a coefficient of exactly 16. To fully isolate the variable u, we must divide both sides of the equation by 16. Dividing the left-hand side by 16 simply cancels the coefficient, leaving only u. Dividing the right-hand side requires us to compute 48 divided by 16. This arithmetic fact confirms that 48 divided by 16 equals exactly 3. We have successfully solved our intermediate equation and found that u equals 3. Although we have found the value of u, we are not yet finished with the math problem. The problem asked us to determine the numerical value of the original variable x. We must recall the algebraic substitution equation that we defined at the very start. We initially defined u as being equal to the square root of x minus 8. We now possess the specific numerical value for this variable u, which is exactly 3. We will substitute the number 3 back into our original defining equation for u. This substitution yields the new equation 3 equals the square root of x minus 8. We must solve this newly formed equation to uncover the final value of the variable x. To isolate the variable x, we must eliminate the square root symbol from the right side. Once again, we use the standard mathematical technique of squaring both sides entirely. We must square the isolated number 3 standing alone on the left side of the equation. Multiplying the integer 3 by itself results in a product of exactly 9. We then square the radical expression situated on the right side of the equals sign. Squaring this particular radical perfectly eliminates the square root symbol completely. This exposes the interior mathematical expression, which is exactly x minus 8. Our current simplified equation is neatly written as 9 equals exactly x minus 8. We are now just one single arithmetic step away from fully isolating the variable x. To isolate x, we reverse the subtraction of 8 that is present on the right side. We accomplish this reversal by adding the integer 8 to both sides of the equation. On the left-hand side, we compute the straightforward sum of the integers 9 and 8. Adding the positive number 9 to the positive number 8 yields a sum of 17. On the right-hand side, the subtracted 8 and the added 8 completely cancel out. This final algebraic cancellation leaves the variable x completely isolated and alone. We have now rigorously determined that the numerical value of x is exactly 17. Because x must be at least 8 to keep the original roots real, this value works fine. This means our final real solution for the original variable x is the number 17. The original problem was the square root of x minus 8 plus a second root. The second root was the square root of x plus 8, and the sum equaled 8. We will now replace every single instance of the variable x with 17. Let us focus our attention on the first radical expression in the equation. We substitute 17 in place of the variable x inside this first radical. This gives us the expression 17 minus 8 inside the square root symbol. We can compute the difference between 17 and 8 using basic subtraction. When we subtract 8 from 17, the resulting integer value is exactly 9. This means the entire first radical term reduces to the square root of 9. The principal square root of the number 9 is equal to the positive integer 3. Now we will shift our focus to the second radical expression in our equation. This second term originally contained the variable x plus the number 8. Once again, we replace the variable x with our calculated value of 17. This produces the expression 17 plus 8 inside the second radical symbol. We must compute the sum of these two integers located inside the square root. Adding the values 17 and 8 together yields a total of 25. This means the entire second radical term reduces to the square root of 25. The principal square root of 25 simplifies to the positive integer 5. We have now successfully simplified both of the radical terms in the equation. The original equation requires us to add these two evaluated results together. We formulate a simple addition problem using our two integer values. We write down the number 3 and we add the number 5 to it. The sum of 3 and 5 gives us a final numerical value of exactly 8. We look back at the right-hand side of the original mathematical equation. The right-hand side was given as the constant numerical value of 8. Our calculated left-hand side perfectly matches the right-hand side value. Both sides of the equation evaluate to the exact same numerical quantity. This rigorous check proves that our solution is mathematically completely sound. Thank you very much for watching this complete mathematical calculation process today. Please consider leaving a like on the video and subscribing to the channel for more math.